So today we have Ziyi Guan talking about her recent work, security bounds for proof-carrying data from Straightline extractors. So take it away.
Okay, so hello everyone, I'm Ziyi. Very happy to be here, like virtually after a few years. And today I'm gonna present my recent paper, Security Bounds for PCDs from Straightline Extractors. This is a recent joint work with my advisor, Alessandro, and Shahan Neilong. So let me start by giving you an overview of what you're going to see today. The first, in the title, we have proof-carrying data. And the first question that some of you might ask is, what is proof-carrying data? And the short answer is that it's a recursive composition of SNARKs. If you never heard of SNARKs, it's okay. We're going to learn it shortly. And PCD has been very useful for efficiently verifying distributed computations. But there's some issue related to PCD. And basically, in practice, PCD is deployed under the assumption that the security of PCD is equal to the security of the underlying SNARK. And the issue is, however, all the existing security analysis show that there is actually a huge gap in the security of these two things. So the PCD is far less secure than the underlying SNARK. So there is no justification of this practice that people has been using in the real world. So in this work, what we show is that we propose an idealized PCD that models hash-based PCD in practice, in which hash-based PCD is a very popular approach that people use to deploy PCD in the real world. And we prove that for this idealized PCD, it is as secure as its underlying SNARK. So it provides somehow a justification for what people have been doing in practice. So, okay, that's a brief overview. Let's forget about those maybe like foreign terms and try to understand things in more detail. So the first question, again, we ask, what is proof-carrying data? And as I just mentioned, proof-carrying data enables distributed parties to perform a distributed computation. And moreover, we would want that the correctness of each step of this distributed computation to be verified efficiently. So let's see a simple example of a distributed computation. It's really simple, just summing 6 numbers. And this is my 6 numbers. My goal is to sum them. And I distribute this work of summing 6 numbers to a panda and a cat. And then, okay, I am lazy. I don't want to sum 6 numbers. So I ask panda and cat to do it for me. But on the other hand, panda is also lazy. So it distributes its own work further to the pink and blue panda. And the blue panda do it one more time. And similarly, the cat also distribute the work. So now that's a distributed computation. And let's see like what would happen if we put this distributed computation into the PCD context. So we have this 3 colorful pandas and 3 colorful cats that are responsible for summing one number that they're given. So it's easy for them. They just output the number itself with the corresponding proof. And in this context, because the task we're given is trivial, so the proof can be empty. But on the other hand, in the more general case that we will see in a minute, this summing operation can be replaced by any other operation you want. And now, and in those contexts, the proofs might not be that trivial. So, okay, let's go back to this picture. We have 6 numbers and 6 proofs. Then the blue panda is gonna aggregate the answer of the yellow and green panda, and at the same time also combine their proof to a proof for the blue panda's computation. And similarly, my panda friend is gonna do the same, and also my cat friend is gonna do the same. Then my job at the end is to sum the number given by my panda and my cat, and at the same time combine their proof. So that's briefly how PCD works and why is it useful. So now let's see it more abstractly. What is the precise theoretical or formal mathematical definition of PCD? So we've seen before, a PCD is always associated with a transcript T for a distributed computation. And here in this example, it's a transcript for a computation of size n equal to h and depth equal to 3. And similar to before, we are able to abstractly determine the correctness of a transcript. And here we use what we call a compliance predicate phi. And let's simply put, this compliance predicate phi is just trying to determine whether the computation is correct. And in our previous example, in the summing context, compliance predicate is just the sum of all the numbers you get. Okay, and we say that a certain node, in this case, the blue node, node 23, is correct if the compliance predicate equal to 1. And on the other hand, the entire transcript is compliant or is correct if every single node inside this transcript is correct. And as we can see in this transcript, in this tree graph, we have a few different letters. We have Z, we have W, and we have pi. And here I'm trying to stick with the classical computational complexity notation, where Z means the instances, W means the witnesses, and pi means the proof. But then the question becomes, okay, in the previous example, we do have the proof, but the proof is actually doing nothing because summing numbers, they can be done very efficiently themselves. So what's the role of the proof actually? So in this context, the proof for this highlighted node 2,3 is gonna provide a proof that first, the computation happened at node 2,3 is correct, and for every child vertex of node 2,3, it has a valid proof string. So now, we are able to formally define the interface of a PCD, which is a proof system. So it contains two algorithms, the prover and the verifier. And the prover is going to take some input. And its input, remember that the prover and the verifier's goal is to prove or verify the computation at each step of this distributed computation shown on the left of this slide. So the prover is going to take the instance and the witness associated to the node, and also the incoming instances and proof from its child vertices. And then it's going to give me pi 2,3, which contains the proof message that is above it. And the verifier is going to get the instance at this node and the proof and decide whether to reject or accept. And of course, since it's a proof system, we have our usual security guarantee of PCD. We have perfect completeness, which is saying that the prover can convince the verifier if the computation is correct. And we also have what we call the knowledge soundness, which is slightly more involved. So it is saying that for every bounded PCD prover, there exists an efficient extractor such that this large probability statement holds. So we don't have to look at the probability expression because we have figures. So the event that we care about is that consider the probability experiment where the bounded prover P output the compliance predicate, the output of the distributed computation and its corresponding proof. And it sent those information to the verifier and the verifier accept. And on the other hand, its corresponding efficient knowledge extractor E gets notice that this E has a subscript P, means that it's a specific extractor for this specific prover. So it has presumably everything it needs to output a transcript corresponding to the computation that the prover is proving for. And we care about the event that the verifier accepts, but the extractor cannot extract a correct computation transcript from the prover's outcome. And we say that notch soundness holds if this event happens with low probability or with probability bounded, upper bounded by kappa. And kappa depends on the security parameter, maximum depth of the computation, and the maximum size of the computation. Okay, so now we know the high level what is a PCD. Then our next natural question is how to construct a PCD. It's a nice notion to have, but we also need to be able to construct it in order for it. Yeah.
So can you hear me? No. Okay. Wait.
Yeah, I guess yeah, it helps if you go closer to the.
Okay, I just
Okay.
wondering, like, if your definition will include like zero knowledge property.
Not really. In this work, we don't really talk about zero knowledge.
Okay. Go ahead. But
Okay.
Zero knowledge easily achievable within PCD.
Actually, there might be a caveat. Last year in Eurocrypt, there is a paper that made the first attempt to valence conjecture, showing that the valence conjecture says that PCD does not exist in the random oracle model. And they, if I remember correctly, but I'm not 100% sure, that paper shows that zero knowledge PCD cannot be achieved in the random oracle model. So in our work, although so far like we are dealing with generic PCD, but in the overview I just mentioned, we actually idealize PCD as PCD in the random oracle model. So it's not maybe the barrier is just this paper about valence conjecture. So I'm actually not sure.
Okay, thank you.
In general, it's easy to add zero knowledge notion to PCD. So if we're working with hash-based PCD or just recursive composition of SNARKs, then yeah, sure, you can add zero knowledge. Okay, so that's some high-level intro to PCD. And now the question becomes how do we actually construct PCDs? And the easy answer here is that PCD can be constructed from a SNARK. And a SNARK is usually defined for a certain NP-complete relations. And here we consider specifically the circuit set relation. What is circuit set? Formally, it takes a circuit C, input X, witness W, and we say that this tuple is in the relation if C evaluates at X and W equal to 1. And we have we can have a SNARK for this C-side relation. In particular, we would have a prover and a verifier, where the prover get both the instance and witness, while the verifier only get the instance. And the prover sends a short proof pi to the verifier, and the verifier decide whether to accept or reject. And again, we would have some security notion that we care about for SNARK. We have our usual perfect completeness, and we also have a corresponding knowledge soundness. And this knowledge soundness is defined similarly. It's defined for every bounded prover, and we say that there exists an efficient extractor such that the following is true. The following event is similar. So the prover output some circuit C, input X and the proof to the verifier accepts, while the extractor gets the information and output a witness. And we say that the event where the verifier accepts but extractor fails is upper bounded by this kappa arg, which depends on the security parameter. Okay, that's a brief review about SNARK. And now we can try to construct PCD. And one naive approach, remember that in the example, in the first overview of PCD, we say that in every single step of the proof need to like try to convince the verifier that the computation happening at this step is correct. At the same time, it also need to show that it has valid proofs for all the incoming computations. So how about we just concatenate all those proofs together, proofs for every single node in the subtree rooted at this node. Let's see how it will go. So we have the PCD prover, and it has the code for the argument or SNARK prover for the compliance predicate phi that is there to check the correctness of the computation. And the PCD proof again gets all the input it needs, and it gives the input to the for the certain node to the argument prover, which provide a proof. And the PCP just take the proof little pi 2-3 for the node 2-3 and concatenate it with the incoming proofs. So this kind of match with our interface. It contains all the proofs that we need. But the issue here is that this big pi 2-3 is not succinct. It grows linearly in the number of vertices rooted in this subtree. And there is no way, like when the tree is not too large, even like reasonably large to be useful, the verifier has no way to efficiently verify the proof, because reading the proof is going to take a very, very long time. So this doesn't work. Then how about recursively composing the SNARK proofs instead of just naively, iteratively concatenate them? So this is actually a working idea. And actually we can say that PCD is a formalization of the recursive proof composition of a SNARK. And basically, what the PCD prover and verifier do is that they invoke the SNARK prover and verifier for a recursive circuit C. And what is this recursive circuit? It's a circuit, and since it's recursive, it is recursive because what part of the input it takes in is the circuit description itself. So it's a circuit that takes its own as input. So that's why we call it a recursive circuit. So itself is part of its input, and also it takes in the instance of the current computation, the witness, and the incoming instances and proofs, Zi's and pi's. And on the other hand, to check the correctness of the computation at a certain node, remember that we say, first, we need to make sure that this particular node is correct. Second, we need to make sure that there is valid proofs for incoming computations. So the first condition can be checked by the compliance predicate by definition, because compliance predicate is responsible for checking the correctness of the proof. And on the other hand, whether there is an accepting or valid proof for incoming nodes can definitely be checked by the argument verifier. So we just give them corresponding input and check whether they accept. And the output of the circuit is going to be the end of the output of all the checks we made inside. So this is the circuit. It is weird because it contains itself is recursive, but still it is a circuit with a relatively short description. So therefore, we can definitely like wrap the SNARK prover and verifier for this recursive circuit inside PCD prover and verifier. So how do we do that? So again, we want to construct the PCD prover. It gets the corresponding input, instance, witness, and also the incoming instances and proofs. It's going to invoke the argument prover. But now the argument prover is trying to prove something about the recursive circuit, which is in turn trying to like testify something about the argument verifier. So now this is kind of like an argument proving a relation about itself. And with the correct input, the argument prover is going to give me some proof, pi. And this pi, I can ask the PCD prover to directly output it and give to the verifier, the PCD verifier. And now the PCD verifier can invoke the argument verifier and decide whether to accept or reject. So does this make sense? There's question, can pause for a few moments because I know this sometimes can be confusing.
Is this a standard way to achieve PCD?
Yes, this is the standard way. So there are also another approach, which is getting PCD from accumulation schemes, but now for this talk today, we just focus on how to get PCD from SNARKs. And that's, I would say that's always the case, like how people get PCD from recursively composing the SNARKs. Okay, if there's no other questions, let's move on. So we've seen the construction. The main topic of our talk is still like the security analysis of PCD. And I mentioned in the first slide that there are previous works that provide some canonical security analysis of PCD. Let's first see how does it work, and then I'll explain why this canonical security analysis is not ideal. Okay, so intuitively, we know that PCD invokes some SNARK, and we want to prove non-soundness of PCD. And then naturally, we would definitely try to connect the non-soundness of PCD with non-soundness of SNARK. And to invoke the non-soundness of SNARK, we have to have argument prover and argument extractor. Remember that non-soundness is defined for every single prover. There exists some extractor such that the event we care about has a probability upper bound. So now let's try to do that. Let's try to get argument provers out of this PCD prover, which is the only algorithm we currently have. And intuitively, we are gonna repeatedly invoke the argument extractor in order to build an extractor for the PCD. Let's see how this works. So I have my PCD prover. PCD prover's output is like that. It's the predicate, the output result, and the output proof. And like, if I just use this PCD prover, I don't get anything because I can't build a transcript. I only have the very top node that contains no information. So now what I do is that I wrap them together and I say that now this is my argument prover, the first argument prover, which outputs Z1 and pi1. And since this argument prover, it conforms with the argument prover interface, I can have a corresponding, I can invoke its corresponding argument extractor, which will give me some witness W1 corresponding to this Z1 and pi1. So now I can say that, okay, I let my first PCD extractor E1 to be just everything that happened before. And E1 is gonna give me some T1, which is a partial tree, which is also something like very, very small. It only has the first node with the first witness and the first output. But still, we are slowly getting there because inside this witness W1, it has information for the next layer. And in particular, it contains information about incoming instances and proofs of this W1 vertex. So now what I do is that I view this next layer as my new argument prover, and I invoke its corresponding extractor. And then I get another set of witnesses for each of those nodes. And now I am able to construct my tree T2. And T2 is much larger. And I finish the extraction for the second layer. And then I just repeat this process until I reach the last layer. And I set my final PCD extractor to be ED. And this works. This give us what we want. We have some security analysis where the notch soundness of the PCD is connected to the notch soundness of the SNARK, because we invoke the SNARK notch soundness for, like, say, D times. But now there is an issue. The issue is that this kind of recursive process of constructing the PCD extractor makes the size of the extractor out of control. Let's see how this happens. So for each argument prover we construct, it invoke the previous PCD extractor EI-1 and some bookkeeping step. And we know by definition that the corresponding argument extractor for this PI has size TE of size of PI. And this means that my PCD extractor EI is upper bounded by the size of the argument extractor for PI plus some bookkeeping step again. And say if this function TE, which is the function that determines the size of the extractor for a specific argument prover, takes some number n and has a polynomial blow up to n to the c, then after the levels of this construction, the final PCD extractor size is going to be p to the c to the d. And this is only polynomial when d is a constant. It cannot, like when d is a super constant, this size of the final extractor is out of control. So this kind of non-black box notch soundness is really problematic because we just simply can't afford the growth of the size of the extractor. It grows exponentially when the depths of the computation increase. And also in practice, the depths of the computation is never constant.
What is C? Like n maps to n to the c? What is the c there?
Arbitrary constant. So here I'm assuming that take an argument extractor, it has certain size. And since we are considering the non-black box notch soundness, so the size of the extractor corresponding to this prover is correspond to some function TE. And here this TE just behaves that it takes the size of the prover and it raises it to the power of C, and that's the size of the corresponding extractor. So see we can view it as some constant.
If C is equal to 1, then there's no blow up, right?
Right. But in general, like we would think C is some large constant because the extractor itself, like the only guarantee we have is that the extractor is somehow efficient in terms of the size of the prover. So in general, C could be large.
Okay. I have a somewhat related question. So when you extract into the trees like this, how do you know what the shape of the tree is?
So if we do the extraction in this way, we always get a tree. So it's possible that actually like the prover has some other computation in mind, but the way I built the extractor, it always extracts a tree that looks like that.
Yeah, but like how do you know that, say, from T1 to T2 that there are free leaves going to the top? Why 3 and not 2 and not 5?
Because from W1, I can parse every information it contains. And W1 contains the information of its incoming nodes. And it's possible like maybe in some other computation transcript that one can construct, this W1 queues actually belongs to the next layer and something like that. Or maybe W21 never has any child vertices anymore, but in this way of defining the extractor, we always get a tree like that.
Okay.
So I'm not saying that this is the only possible transcript that can correspond to this prover's output, but we only need to exhibit one of them.
Okay. So it's not a problem if the tree that we extract is not the tree that we started with the tree that like the honest prover or whatever decided to.
So extractor only makes sense when we deal with malicious prover, and the honest prover is like another story. Like so basically, in the context of trying to prove knowledge soundness, we always consider malicious prover. And malicious prover can, yes, for sure, it can also follow the honest prover to build a tree or to build a computation. It doesn't have to be a tree, actually. It can also be a DAG. But no matter what it is, the way that we do the construction always give us the tree, this particular kind of tree.
Okay. Yeah. I guess sorry to keep asking, but if the tree that we extract is not, say, the way that the malicious prover got to the final result, then what does it even mean to have?
We don't care about the shape of the tree. We just care about at each node in the tree whether the computation is done correctly. That's the only thing we care about. And it's possible that the prover has some other trees, but like, for example, in this graph, we are invoking the argument extractor, right? And the argument extractor can do crazy things. It can be randomized, for example.
Yeah.
So if the argument extractor is randomized, even if I'm running the same PC extractor that I construct, every time I might get a different tree.
Okay.
But still, like the tree, like I output the tree, and I just need to make sure that first the tree's output is Z1, and also the tree's output proof is pi1. And also inside the tree, every single node is computed correctly, and that's enough. That means that I have a computation of certain size that conform to the size limit or the depth limit, and this tree is a correct computation of something, and its output is Z1 and pi1, which is actually the only information I get. So there's no guarantee that I'm gonna get the same tree as the prover imagined. Or maybe the prover doesn't even have a tree.
Okay, thanks.
Okay. So we're saying that, okay, this kind of analysis is problematic because the size grows too quickly. And actually, even now, finding a better analysis in this regime, this non-black box knowledge soundness regime, still remains a major open problem in this era. It would be great if someone can solve it, but we just don't know how. But today, instead of trying to solve this open problem, we focus on PCD based on SNARKs with a stronger notion of extraction. So let's see actually like what exactly we show. So that's our main theorem. And we prove a significantly improved security bound for PCD based on SNARKs with straightline extraction. And straightline extraction is what I hinted on the previous slide, the stronger notion of knowledge extraction. And what we did is that we consider a SNARK for C set with straightline extraction. We do the same auto recursive proof composition. We get the PCD with straightline extraction. It doesn't matter too much at this point what straightline extraction means. We just need to know that it's stronger. And what we proved is actually that the knowledge soundness of the PCD is less than or equal to the knowledge soundness of the argument. So this is the thing we hoped for, the best we can do, basically. And compared to what was done previously in prior works, what they did was that they take a SNARK for C set, they compose it to get a PCD, and it was, as we've seen before, there is no security when D is larger than constant. So in general, the caveat here is that in practice, SNARKs have non-black box knowledge soundness. And straightline extraction, it's nice, but it only exists in idealized models. Then in this case, we should ask, how can we apply our theorem in practice then? Like, how do we keep our promise that we provide some justification for the deployments that's happening in practice? So let's answer this question. So the main application of our theorem, as mentioned before, is how to set parameters for real life PCD. So we propose a new idealization of hash-based PCD used in practice as a PCD in the ROM. And this PCD is in quote because it's not exactly a PCD. We will get to this later. And then in this case, we can apply our theorem. And in general, we say that the notch soundness for the PCD is no worse than the notch soundness of the argument. And especially in the case for random oracle, we get something even better. Inside the argument notch soundness, we don't pay for the n, which is the size of the computation. Because why would this n show up? Remember that in the previous slide, in the canonical security analysis, we were like trying to prove things by constructing argument prover from PCD prover. And by doing that, we kind of invoke the argument prover for n times, which is the number of nodes in the transcript. So naturally, like this n shows up somewhere like in the argument prover size, but in the random oracle model, we don't pay for it. So this gives the first justification of the current choice of parameters in practice. And there are actually a few deployments of hash-based PCDs in practice. And on the other hand, our theorem also has some more, I would say, theoretical implications. The first application is that 15 years or 14 years ago, CT10 constructed a SNARK with straight line extraction in a certain oracle model. And what they prove is that notch soundness of PCDs are bounded by n times the argument notch soundness. And our theorem just improved their bound by removing this multiplicative n factor. Similar things happened to a paper that come up last year. And again, they have a SNARK with straight line extraction, and they have a similar analysis. Our bunch again improved their bunch. Okay.
Would you repeat the intuition of why you don't have that n loss? Yeah, the factor of n loss.
In the random oracle model?
So yeah.
So we will get to that later. It's actually part of the security analysis. And I'll talk about it in a second.
Can you explain your notation? Oh, there's also a question in the chat.
Okay, I can't open chat, so
That's okay. Let me open it. So question is a hash-based PCD a Mikali SNARK, i.e. PCD and random oracle model?
So you can think of hash-based PCD as recursive composition of hash-based SNARK. And yes, usually people would use SNARKs like Mikali SNARK or its IOP version, the BCS SNARK, or some variants of it. Does that answer the question?
Yes, yes.
Okay. Okay. And then
explain your notation here. So when you write, say, kappa arc of lambda, q, and n, what does that mean?
So sorry, my cat just jumped. That's that thing when you do presentation at home. Okay, so the argument notch soundness, it depends on a few parameters. Because again, we're in the oracle models, we measure the runtime of or we measure the size of the algorithm by its query complexity to the oracle, and also when we need to use crypto, like signature scheme or automatization is in application 2 and 3 here, we also care about the circuit size of the algorithm. So here, lambda is the security parameter, which makes sense, and q is the maximum number of query the algorithm or the malicious prover can make to the oracle function, and n is the circuit size of the malicious prover. So notch depends on those parameters because it's not information theoretic, so it depends on the how bounded the adversary is.
I see. this big N, is it related to the size of the PCD transcript that you will extract?
Yes. Yes.
So is it both the size of the malicious prover and the size of the PCD transcript? Or
The size of the malicious okay, sorry about it's not the best notation, but in this case, remember that in the previous canonical security analysis, we construct like a few argument provers, right? And then we can have very easy upper bound on the size of the argument prover, which is the number of nodes or vertices each extracted before that. And here I use this n in kappa arg just to mean that the size of the argument adversary might depend on n, which is the size of the transcript that the argument prover is going to deal with. Maybe I should actually change it to something like size and say that size is a function of n. That would maybe be more clear.
okay, thanks. And I guess final comments. I don't think Mina is doing hash-based PCD. It's using like a Halo style PCD with accumulation.
Okay, that I didn't know. I'll double check. Thank you. Okay, so if there's no other questions, we can actually take some time to explain more about the stronger non-soundness guarantee, the straight-line extraction. And also we don't have all the time, so I'll try to skip a few slides just so that we can get to the more important point. So SNARK with straight-line extractions, we mentioned that they happens only for SNARKs in oracle models, for example, in the random oracle model. And it behaves very similar to a normal SNARK, but now it's just that it has oracle access, but everything else didn't change. And then it has this very strong straight-line non-soundness, which is saying that there exists a universal deterministic extractor that works for every single bounded argument adversary prover. And then the event we care about is almost identical. Prover outputs something, and the extractor fails, but the verifier accepts. That's the event that we care about. But now it's really important that we have the explicit universal extractor that works for every single prover. And a wonderful fact is that in the random oracle model and a few other oracle models, there are SNARKs that with the straight-line extraction, like Mikali SNARK and BCS SNARK. Okay, so now let's see whether we can use the generic recursive composition technique to compose SNARKs with straight-line extraction. If we can, then we're happy, like there is no issue here. Let's see. We have the original recursive circuit, but now everything has oracle access to the oracle function. And then we have our old good prover verifier construction, although everyone has oracle access. Then the only issue that happened is that the circuit C, recursive circuit, now has oracle access. So the prover and the argument prover and verifier, they need to prove compositions. They need to prove computations involving the oracle, which they can't. They can't do it because it's it's not written in the relation that they claim to be able to prove or verify. So what we need is actually SNARK in the oracle model that can prove or verify for oracle relations, which we call relativized SNARK. And oracle relations just the same relation, but now it's just the circuit has oracle access. And now everything works fine. We're able to take relativized SNARK and recursively compose it to get a PCD. So now nothing is broken. And also what we get from this good relativized SNARK is that we get a resulting PCD also with this strong straight line non-soundness notion, which again, we have a universal knowledge extractor that works for every prover. Okay, so that's our way of constructing PCD from relativized SNARK. And now this is, I guess, the more exciting part. How did we achieve our security analysis that doesn't pay for the size blowup? So in general, we first, in order to prove knowledge soundness, we first need to prove, we need to construct the PCD extractor. Now, how is PCD extractor constructed? Like, by its interface, it takes the prover's output and also the trace, which is the query answer trace of the prover's queries to the oracle. And it goes to produce a transcript. So it starts by taking the prover's output, producing this dummy tree, which has only one dummy node and one root. And it initializes an extraction queue, which contains only the root, v1. And it runs the argument extractor, get the witness associated with v1, and it parse v1 as before, and get all its incoming vertices. And now it expands its extraction queue by adding all those new vertices to the queue. And it runs the argument extractor one by one. And at the end, it's going to be able to finish. So now the extractor just do the extraction in one pass instead of like have to do this recursion between prover construction, extractor construction. Now it's much easier to construct. And this is the very, very natural construction of PCD extractor. And actually, because of the time, maybe I want to skip the security analysis in previous work, because just intuitively, a very natural analysis would give you the sponge, which has a multiplicative factor of n, because each recursion, it just pays for the, you have to pay for the knowledge soundness error of the argument. So recall that in the way of building this tree in the previous slide, every single time we invoke the extractor, a natural analysis would pay for the error associated with each invocation of the argument extractor. So that's how this multiplicative factor n shows up. I'm gonna skip that. So the focus I wanted to be our security analysis. And the intuition of the analysis is that this is how our extractor works. Takes the prover's output and output a computation transcript. And notice that we care about the event where T is not compliant. T is incorrect, which means that there exists one vertex in T that is not correct. And we can find such vertex in one pass and output it. We don't have to try to pay for error for each vertices because not all vertices are bad. Or in other words, at some point, if we follow the order of the extractor, we're gonna hit the first vertex that is bad, and we output this vertex and we're done. We don't have to run the following, we don't have to run the rest. Because there's already one bad vertex, that means that the transcript is bad already. So in this case, this more like one pass analysis give us that the PCD knowledge soundness does not have this multiplicative blow up in terms of the argument knowledge soundness. And actually, yes, I'm gonna use 1 minute to try to do a more careful analysis. So our goal is to take the PCD prover and construct an argument prover that output a problematic vertex. What do we do? The only thing we can do is that we need to ask the argument prover to run the extractor and locate the problematic vertex. And since recall that the extractor is deterministic in the straight line world, the argument prover can definitely do it. It can follow the extractor's path, but only with one additional check. And this additional check is actually check whether at certain location, at certain node, when it's trying to extract whether the recursive circuit accept or reject. And in the case that the recursive circuit reject, we have to recall that in the notch soundness event, the PCD verifier accept, which means that the argument verifier also accept. So in this case, we have a problematic vertex in the argument term, and we pay it once, and we never look at the rest of the transcript. So in this case, we get our theorem. We don't pay for the multiplicative factor. But again, in this case, there is this little this n factor inside the parenthesis, which is caused by the fact that the argument prover has to run the extractor, which extract at most n vertices. So this is a bit fast. I hope at least it makes sense in an intuitive level. So if there is no question, I'm gonna take the last few minutes and explain how we can use our theorem in practice to set security for hash-based PCD. Okay, so let's first do a warm-up. How do we set parameters for hash-based SNARKs? So this is some very established three-step recipe. We model the hash function as some ideal function, a random function, and we idealize hash-based SNARK as a SNARK in the random oracle model, what we call ROM SNARK. So like that. And we establish concrete security bound for ROM SNARK. And then we set security parameters for the original hash-based SNARK according to our concrete security bound. But we have to be careful here, because this step of idealization is applicable only when the SNARK has black box use of the hash function. But fortunately, this is the case for the hash-based SNARKs that we care about. For example, the Mikali SNARKs or all the SNARKs in Mikali family. Okay, so now the question is, can we do something similar for hash-based PCD? And in general, like PCD are deployed based on different approaches in practice. One of the very popular ones, hash-based PCD. And what we want to do.
Question in the chats. So don't we have to concretely instantiate the ROM for recursive SNARKs composition, which makes the overall SNARK to be heuristic, even in the random oracle model?
Okay, maybe I'll.
So I think it's like saying, with recursive composition, you have to make non-black box use of the hash function, which somewhat invalidates the random oracle heuristic. Is that what you meant in the question? Okay, yeah.
Okay. So I guess the answer here is that this is exactly the reason why we have to use relativized SNARK instead of just SNARK. So relativized SNARK is SNARK that can that can prove relationship about the oracle itself. So in this case, yes, normal SNARK in the ROM should not work, but relativized SNARK does. Does that roughly answer your question?
Yeah, I think that's.
Okay, so let me. Okay, I'll try to finish in 2 minutes. So we want to do something similar to set parameter for hash-based PCD. So in the standard model, we consider hash-based PCD, which is achieved by hash-based SNARK and recursive proof composition. And we have this idealization of the hash-based SNARK in the random oracle model. But then the issue is what we actually mentioned before. This analysis is very, very expensive. The extractor size blows up. So, but nevertheless, like in practice, people still use hash-based PCD as if it's as secure as the underlying SNARK. So the question is, can our new analysis justify this parameter regime? So recall that our analysis shows that for relativized SNARK, if if you do recursive proof composition, you get PCD. And you don't pay for, you don't have expensive security analysis. So in this case, the thing missing here is that we somehow need to connect things together. We need to connect hash-based PCD with Straightline extraction and hash-based SNARK with relativized SNARK. So then another idea is that maybe how about take hash-based PCD, idealize it to PCD in the ROM, and do recursive proof composition from relativized SNARK. And then we can apply our theorem. And the first thing that is going to break is actually what happened, what I think related to what was asked in the chat. Idealization here is applicable only if the hash function is used in a black box way, which for PCD is not true in general. And moreover, something like more fundamental is broken as well. So relativized SNARK in the ROM is not believed to exist, and PCD in the ROM is not believed to exist. So in general, we just can't apply our theorem. So what do? We propose a new idealization. Recall that the issue is this non-black box use of hash function. And we observe that actually PCD do look at the hash function, but it only look at it to check the correctness. It doesn't like go inside the hash function and destroy it or change its code or do something crazy. And on the other hand, the issue is caused by the fact that this recursive circuit C is an oracle circuit because the argument verifier makes oracle queries. So our solution is that why don't we forward all the queries made by this recursive circuit C by asking the argument prover to attach C's query answer trace in the proof? Of course, like forwarding the queries may make the proof non-succinct anymore, but it's justifiable because at the same time, we know that PCD doesn't look at the hash function and try to do anything bad. It's just checking the query answer trace in reality. So in this case, if we consider this new idealization, we can take hash-based PCD, idealize it to some non-succinct PCD in the ROM, but with Straightline extraction, which can be get from some non-succinct relativized SNARK in the ROM by recursive composition. And in this case, our theorem apply. And actually, since everything is in the ROM, so we don't even pay for this prover size blow up inside the parentheses, because in the ROM, the notch soundness does not depend on the size of the prover. It only depends on the query bound of the prover. So we're happy we are able to use our theorem. And I'm gonna skip the last step, but show the quick recap of what we talked about today. And thank you for coming. Feel free to ask any questions if you still have any.
Thank you for the talk. Any questions? Cool. Let me stop recording.